Okay, so hello, good morning, everyone. So thank you for the introduction again, and let's discuss now how to compute Hubbard parameters or how to determine them. Okay, I don't want to spend too much time on what Matteo already discussed. Let me just some quick summary. Yeah, so in DFT+U, the total energy is the sum of the DFT energy, computed, let's say, with LDA or GGA, plus the Hubbard term. This is the on-site correction, where U is the Hubbard parameter. It's a constant. Then we have trace because we're working with matrices, and N is the atomic occupation matrix. It depends on atomic index I, spin sigma, and magnetic quantum numbers N1 and N2. And this object is defined as the sum over I, which are the constraint states. F are Fermi-Dirac or other occupations of constraint states. And then we have projection of constraint wave functions onto the localized functions, which are atom-centered. This could be atomic orbitals or Wannier functions or other. I will talk more about this later. So originally, DFT+U was introduced in the early 90s, as Matteo already said, and it was inspired by the Hubbard model. So basically, you take DFT and you merge it with the Hubbard model, you get DFT+U. It was heuristic. There is no theorem, unfortunately. So that's why many people see this method is like a bit, let's say, semi-empirical. If there was a theorem, that would be much more powerful and justified. And also, we don't know the value of the Hubbard U parameter. So when people introduced this method, they didn't know how to define or determine the U values. And so what the U term does, it actually localizes electrons, as Matteo just described. If in DFT, due to self-interaction errors, you have electrons delocalized, like typically DNF, which are delocalized. And with +U correction, you localize them more. And then later, Matteo and Campo, they generalized DFT+U to DFT+U+V, where you have not only the localized on-site term, which wants to localize electrons, but there is also another term, inter-site, that wants to actually restore the hybridization with ligands. So you see that while +U wants to localize electrons, but +V restores hybridization with neighboring ligands if there are some degree of covalence. So this framework is more flexible, more generalized, more degrees of freedom to play with. So it's more powerful. Okay, so there are two important points to remember when you want to use DFT+U or DFT+U+V. On the one hand, you have the Hubbard parameters that you have to determine somehow because they are not given by theory. And on the other hand, also, there are different ways how you choose the localized functions onto which you project, because there is no unique definition. You can have different localized functions. So let's talk a little bit more about these 2 points. So, okay, let's start with the Hubbard parameters. This is really the key. When you want to use DFT+U, it's really the most important thing you need to take care of. There are 2 strategies. One is the semi-empirical one, where you sort of try to guess Hubbard U or try to tune it to reproduce some experimental properties of interests, such as band gaps, magnetic moments, lattice parameters, oxidation enthalpies. But if you want to follow this path, you need to have a reference experimental data. But this method is really, really popular because it's very, let's say, simple. But what would you do if you don't have experimental data? Let's say we have some exotic material for which you don't know. There is no experimental data yet. So what would you do? So typically people try to, let's say, use U from other materials which are similar to the one you want to study, but then it's not really rigorous and very precise. And the other possibility is to really follow the first principle path when you can compute Hubbard U and V. And there are different methods around. Like one of them is the constrained density functional theory, CRPA, which is the constrained random phase approximation, Hartree-Fock based approaches, let's say ACBN0 functional, linear response theory, maybe some other. So there are plenty of methods, all of them with different results. And so, yeah, what to do? So we're actually next year, we're trying to organize a workshop where we want to gather really people from different groups who use different methods and try really to discuss and brainstorm what are the differences and similarities between methods, etc. Because it's really confusing. And in this talk, I'm gonna focus only on one of them, which is linear response theory. And this method was proposed by Matteo and Stefano. All right, so very important slide. I think this is the most important, in my opinion. So Hubbard parameters are not universal. What does this mean? If you want to compute Hubbard parameters, they depend on many factors. One of them is the type of Hubbard projector functions that you choose. This is highlighted in yellow. As you remember, atomic occupation matrices are defined by projecting Poincare functions onto localized orbitals, and there is no unique way how to choose them. In different codes, you have different options. Let's say in Quantum ESPRESSO, we have some types of Hubbard projector functions. In ABID, it's another, in VASP, it's another, in VN2K, CSPA. Different codes have different options. And so, let's say in Quantum ESPRESSO, we have atomic orbitals, orthogonalized one. Now we're working on maximally localized linear functions, but there are many other options. And so depending on which type of projector functions you use, you would need different values of U. The other factor is the pseudopotential and oxidation state. So if you use, let's say for iron, different pseudopotentials, you would need slightly different U parameter, even not slight. If you have semi-core states, the U parameter can change by 1 eV or more. Then exchange correlation functional, depending on what are you doing, like LDA plus U or GGA plus U or meta GGA plus U would need different value of U. And then self-consistency, because there are let's say two ways how to compute Hubbard U. One is the one shot, and another self-consistent. I will explain at the end of my talk what it was doing. And by the way, historically, the method was called LDA plus U, because in the early 90s, the original authors, they used LDA as a basis functional. So that's why historically it's called LDA plus U. But nowadays, people use also GGA plus U. And in GGA, you can have PBE, so PBE plus U, PBE sol plus U, etc. But now also people use SCAN plus U. So actually, we're trying to shift from the old historically proposed name LDA plus U to more general, which is DFT plus U and DFT plus U plus V. So yes, see, there are many factors, and the U parameter depends on all of them. So U is not universal at all. Now, so how do we compute Hubbard U using one of the first principles methods, which is linear response? Let's start again with the definition of the energy functional. Here I simplified a bit the equation. You see there is no summation over atoms. For simplicity, just to explain the concept, let's say there is one conditional metal atom. And bold N is the matrix. So it's not a number, it's a matrix. And if we take the trace of this matrix, which is the sum of the diagonal elements, we obtain a number. It's a scalar N. And this scalar N tells you how many electrons are sitting on, let's say, 3D shell of iron. This is very useful information. And this is what Matteo mentioned closer to the end of his talk, that DFT plus U and plus V, they actually cure self-interactions. They don't cure strong correlations. And so in this figure, we are seeing the total energy as a function of the number of electrons in the Hubbard manifold. So it's not total number of electrons in the system, but it's the number of electrons in the Hubbard manifold. And the exact behavior must be piecewise linear. And this is very important. This is heuristic. This is not a theorem or anything. It's just really heuristic statement that the number of electrons in the Hubbard manifold is piecewise linear. Approximate DFT gives you quadratic-like behavior due to self-interaction errors. And with Hubbard corrections, plus U or plus U plus V, we are restoring the piecewise linear behavior. So we're adding to our DFT functional a correction, Hubbard correction, to remove this, to compensate for this unphysical curvature. And so based on this observation, we can define Hubbard U in the following way. So what we are requiring is that the second derivative of the total energy must be, with respect to the occupations, this one, must be 0. So the second derivative means that there is zero curvature. There is no curvature. So it means if this condition is satisfied, we have a straight line. And this is exactly what we want. So we want this condition to be satisfied. So we go back to our expression and simply take the second derivative. It's a very simple exercise. So if you take second derivative of this, you simply have 1 minus, 1 times n minus n squared. So the second derivative will kill the first term, and from the minus n squared, you will have just minus, and factor of 2 will cancel with this. You have just minus u, and here you have second derivative DFT energy. So you have this definition, very simple definition. And actually, another thing that I would like to highlight, if you actually examine this expression, it's very interesting because what this correction does, it removes the quadratic term. So you remove n squared, so you remove this parabolic-like behavior, and you're adding plus 1 times n. So they're putting in the linear behavior. So it's very interesting. Actually, this was derived starting from Hubbard model. We have Hubbard-like term minus double counting term in the fully localized limit. But very interestingly, that the final expression has a lot of physical sense and meaning. And actually nowadays, and actually, some time ago, Kulik and Marzar and other researchers, they actually realized that this can be actually derived from a different perspective, not thinking about the Hubbard model, but actually from the perspective of restoring the piecewise linearity. Okay, so let's move on. We have the definition of Hubbard U, and now how to use this definition in practice. So there is a little problem actually here, because here we want to compute the derivative of the DFT energy with respect to the occupations, but this DFT energy does not depend explicitly on occupations, because DFT is the function of the density, not of the occupations. So we cannot straightforwardly compute this object. So we need to do some math. And actually Stefano and Matteo, they did it in 2005, actually earlier. So it's very clean and simple and elegant. So we start with our DFT energy functional, which depends on, is a functional of the spin density, spin charge density rho sigma. We're adding a term, some of our atomic sites, lambda are coefficients, and are the occupation numbers. And we want to minimize this sum of these two terms with respect to the spin charge density. And we call this new object E of lambda parameter. So this is a Legendre transformation and minimization of this expression with respect to the spin charge density. And then we construct another object. So we take this E of lambda and we subtract back the term that we added before. And we call this new object E bar, which now explicitly depends on occupations. And this is it essentially. Now we can compute the derivative of this object E bar with respect to n, and this gives us minus lambda. But we need second derivative. Let's take another one. So the second derivative gives us minus d lambda over dn, and we call this object minus chi to the power minus 1. So chi is called susceptibility or response matrix. And then we can define our U as this object minus chi to the power minus 1. And here we do some ansatz. We're subtracting another term, which is similar to the first one. So what is this? So the first term, chi, is the self-consistent susceptibility, while this term is called the bare term. So why do we subtract it? Because this term is not related to electron-electron interactions. And then we can massage them and obtain chi naught minus 1 minus chi minus 1. So let me rewrite this expression in a different form. So this is a Dyson equation. So maybe this will be easier for you to understand and justify why there is chi naught here. Because I mean, those of you who work with spectroscopies to compute absorption spectra or electron and Joule spectra, you know, you're familiar with Dyson equation. There, instead of U, here you have F exchange correlations. exchange hard in exchange correlation kernel, but in our case we have the Hubbard U here, which is the strength of electron-electron interactions. Okay, so this is the definition of Hubbard U. And how to use it in practice is very simple. You can take your favorite electronic structure code, be it Quantum ESPRESSO or WASP or Abinit or you name it. And then you just take your DFT solver, Conchem equation, and you simply plug in extra term, which is the perturbation. So this is called modified Conchem equation. We just insert in here the term where lambda is the strength of the perturbation, it's a constant, and V is the perturbing potential. It's defined as the projector on the Hubbard manifold. And then you solve this equation for a few values of lambda. 2 values is sufficient. You just take infinitesimal small value, typically positive and negative. Why we do this? Because then we want to use finite differences to compute the response matrices. So basically you solve this equation for 2 values of lambda, close to 0. And then you see essentially the linear response of the occupations to such a perturbation. So you take a supercell. I'll explain in a second why supercell. You take a supercell and you perturb, say, this atom in the center of the octahedron. So you apply this perturbation. It's a potential, it's a rigid shift of electronic states. And then you see how all the rest of the system reacts to this small perturbation. And you compute the response of all atoms, occupations of all atoms, and you build this response matrix. And then from this chi in chi naught, in a similar way, you can compute the U and V. So U is the diagonal elements of this resulting matrix, while V is the off diagonal. So why do we use supercell? Because it's like when you deal with defects in periodic boundary conditions, this perturbed atom will be repeated in 3 dimensions here, there, and over there. So if you work with the primitive cell, the perturbed atom will interact with this periodic replica and will lead to unphysical interactions. So we want to avoid that. So we build a supercell and we increase the size of the supercell until the interaction between this atom and its replica is vanishing. And this approach is very simple. So that's why if you see how many times this paper was cited, I think it's more than 2,000. So many groups use this approach. It's really simple. Just modify Conchem equation. But you need to do some post-processing. So it's a little bit can be involved. Nevertheless, you can write tweet and deal with that. So since we need to build supercells, it's computationally expensive. And sometimes you can have convergence issues because it's harder to converge supercells than in primitive cells. And then, as I said, it can be quite cumbersome to use in practice. Okay, so then when I moved to EPFL in 2016, Matteo and Nicola say they have a nice idea how to reformulate this approach using density function perturbation theory that we learned about yesterday opponents. So it's okay, let's use DFPT for this problem. And let me explain the basic concept behind this. So this is, let's say, we are in 2 dimensions and we have a square lattice. This is our primitive cell. Small a is the length, is the lattice parameter. And then we can build a 2x2 supercell. So capital A is the length of this supercell lattice parameter. And the supercell can be L1, L2, L3. Here we just take 2x2. Now, what about the brilliant zones? As you know, if you have small cell in real space, you have big brilliant zone in reciprocal space and vice versa. If you have big cell in real space, in reciprocal space, you have small brilliant zone. So if we define B, small b as the reciprocal lattice vector, the size of this brilliant zone, so the capital B would be the corresponding reciprocal lattice vector for this brilliant zone. And this is L times smaller than small b. And then we can also define generic reciprocal lattice vectors like small g and capital G. And this small g is defined in terms of B1, B2, B3, and where K prime, L prime, M prime are integer numbers. And same for G, capital G. They can be defined in terms of B1, B2, B2, B3. Okay, this is very basic. So why do I'm talking about this? This is to explain the concept on this slide. So let's recall capital G here. And then we use the definition of capital B for the red Brillouin zone. And we put this definition inside, we obtain this expression. And here we are making ansatz. We can define these integers k, l, and m this way, where in green I highlight quotients. It's k prime, l prime, and prime, which are also integers. And in magenta, I define k bar, l bar, m bar, which are remainders. So if we use this ansatz and we plug this here, we can rewrite our capital G as a sum of the small g plus some q vector. So this is really it's the basis. I recall that the small g is defined in terms of the B1, B2, B3, the small one. And here we get the definition of the q vector. It's defined using these remainders divided by L1, L2, L3, and B1. So we rewrote the generic reciprocal lattice vector for the Brillouin zone of the supercell in terms of reciprocal lattice vector of the Brillouin zone of the primitive cell plus some generic q vector. And this is important for this slide, how to switch from supercells to primitive cells. This is our purpose. So we can also consider potential of the supercell, V of R. We can write it using Fourier transform, sum over reciprocal lattice vectors, the phase factor, and the Fourier coefficients. And then we put indices to be more precise. And then we use the definition of capital G of the previous slide, small g plus q. So if we put this definition in here and do some manipulations, we can rewrite our potential in a supercell as sum over q vectors or q points, some phase factors, and the new object v bar of q, which is defined here by summing up over reciprocal lattice vector of the primitive Brillouin zone of the primitive cell. So this is very useful. Yeah, before I go here, this is very useful because what we're trying to do here is to represent the potential in a supercell in terms of sum over monochromatic perturbations or monochromatic components for the primitive cell. So we're shifting from supercell to primitive cell, but the price to pay is that in the supercell we have this gamma point perturbation, while in the primitive cell we would have many monochromatic perturbations. So I'll explain on the next slide. So this is the final slide to explain the shift from supercell to primitive cell. So this is our original modified Conjugate equation and the perturbing potential. And we're using here the perturbation theory to first order, and we expand in Taylor series all quantities here, like Hamiltonian, wave function, and eigenvalues. So we expand in Taylor series to first order, and we can end up with this first order equation, where the psi over the lambda are first order variations of Poincare wave functions due to perturbation. We can call them response wave functions. And this is the response Hart exchange correlation potential, response of eigenvalues. And this is analytical expression, which is implemented in quantum express and can be used in place of this modified Conjugate equation. Then we use this concept of rewriting potential as a sum over monochromatic components, that the math of the previous 3 slides. And finally, we can compute the final object of interest, the response matrix. Instead of using finite differences, we're using analytical expression defined as the sum over monochromatic components, sum over q, some phase factor, and this is the monochromatic lattice periodic objects which depend on the wave vector of q. So what we did here, first we rewrote our modified equation in terms of using perturbation theory to first order, and second, we go from supercell to primitive cell. So there are two steps here, because we can solve this equation even for the supercell. So there are two steps here. And this is, of course, not new, because DFPT was developed in late 80s, early 90s, by Paolo, Stefano, Andrea Del Corso, and later by Gons and workers. So DFPT was introduced first in the context of phonos, but it's actually very general, can be applied to many other problems. And here I'm talking about Hubbard parameters. Tomorrow, Nicola will talk applying DFPT to compute Koopmans, screening coefficients. So it's very general. Well, historically, it was proposed for phonos. Here we are like 30 years later, we apply it for computing Hubbard parameters, and then Koopmans, and we can maybe apply it to other problems. So we give the credit to the original authors, of course. So this approach is very nice because it's computationally less expensive. As Stefan mentioned, I think on Monday, the computational cost is lower because now we're having linear scaling with respect to the number of Q points. So we have fewer atoms, but we have more Q points, but it's linear scaling with respect to Q, and Q still cube with respect to the number of atoms. While in the old approach, you have that gamma point perturbation, but you have a supercell. So you have a huge number of atoms to the power of 3. So you're really gaining a lot in terms of scaling. Then it's easier to converge because you're dealing with primitive cells. And we implemented it in Quantum ESPRESSO. It's user-friendly and autonomous. These are the basic papers documenting the theory and the code in Quantum ESPRESSO. Just to really convince you that we gain in terms of computational cost. This is the CPU time as a function of the number of NQ, which is the number of Q points in the DFPT approach, or equivalently at the size of the supercell in the old approach. And we can see that for the size of the supercell 4 by 4 by 4, if you replace this old approach by the new one, you're gaining a factor of 52 speed up. This is really huge. And moreover, the nice thing about DFPT with Q points is that we can use symmetry. We can reduce number of Q points using symmetry. While in the old approach, you cannot use this trick because you have a supercell with a certain number of atoms. You can't reduce number of atoms. Well, here we have better scaling on top of that, thanks to the symmetry, we have fewer calculations. This is really enormous speed up. And again, to prove that this is working, in this table, I show you the comparison of the old linear response supercell approach with the new DFPT approach. And you see that the resulting U values are essentially the same. This is some numerical noise, but we can reduce this difference even more if we use higher cutoff and other convergence parameters. Okay, so if you want to use this approach in practice, you need to converge Hubbard U with respect to many parameters like cutoff. But on this slide, I want to show you that the Hubbard U must be converged with respect to the K mesh and Q mesh. As any other property, U must be converged. And here you see how the Hubbard U changes if you compute it using different K meshes and Q meshes. And from this convergence test, I would conclude that the converged U is 8.18 EV using this K mesh and this Q mesh. Again, when you talk about convergence, you need to say which is the threshold. Here, I guess, I don't remember, but probably I took 0.01 EV or something like that. And for that accuracy of U, I need these meshes. So again, if you want to use it for your research, remember to converge Hubbard parameters with respect to K mesh, Q mesh, and cutoff. So that was all about Hubbard parameters. I finish soon. How much time do I have?
I think it's still 10 minutes.
Or maybe I have a few minutes. So that was about Hubbard parameters, but as I told you, also there are different ways how to define Hubbard projectors. So there is a zoo of Hubbard projectors. In Quantum ESPRESSO, we have 3 options. The first 2 are already available since a long time. The third one is in progress. So the first one is using non-orthogonalized atomic orbitals, phi, which are provided with pseudopotentials. Second option, if you can do something more complicated than that, you can use loading orthogonalization method. So you compute the overlap matrix between neighboring orbitals, and then you invert this matrix and take square roots, and then you take linear combination of these inverted objects with the original non-orthogonalized orbitals, and you call it phi tilde. It's our new orbitals which are orthogonalized. And finally, on Monday, you learned about maximal Lagrangian functions. So we're working also on implementing this possibility in Quantum ESPRESSO. In fact, if you use different Hubbard projectors, you will have different values of U. If we take, this is what I'm saying, the U and V values will be different. If you take nickel oxide and try to use different projectors, you would have different values. Let's say you go from 6.76 to 7.43, which is not negligible, of course. And for V, it's a huge change from 1.25 to 0.37. And I hope you will remember after my talk that it is crucial to keep consistency between Hubbard parameters and Hubbard projectors. This means that if you choose this type of Hubbard projectors and you compute U, so you need to use these values of U and V with the same type of projectors when you run production calculations, let's say band structure, high density, etc. So you should not mix, let's say you compute U and V with this type of projectors, but then you use another type of projector. You should not mix. If you do that, you are in trouble, and I'm showing it here on this slide. So in green, I highlight the correct way to proceed. You are consistent, use U and V computed with orthoatomic orbitals, and then you run calculations with the same type of projectors, and you obtain voltages. So I take example of batteries and voltages by following Matteo. So you see, if you use consistently U and V with the same type of projectors, you are close to experiments. But if you start mixing things, let's say you compute U and V with orthoatomic orbitals, but then you perform structural optimization with non-orthogonalized orbitals, but that values of U and V, you would have voltages which are much off respect to the experimental value. And so, sorry, this is for the lattice parameter, apologies, and this is for the voltage. Okay, I'm just finishing my slides. So at the beginning, I mentioned that I can compute Hubbard parameters either in one shot or self-consistently. So one shot, it means you just start with your experimental geometry with initial values that will be 0 because you don't know them. You run the ground state calculation with the pw.x code of Quantum ESPRESSO. You used our approach, DFPT, to compute U and V. And then you can stop there. You say, okay, this is my one-shot U and V values, and I stop here. But you can do better than that, and actually you should do better than that. Then you can do structural optimization with these U and V values, because now your geometry is optimized using U and V corrections. But then you can go back and continue this loop until convergence. So why do you do that? Because if you do this self-consistently, you are trying to achieve the scenario when your geometry is consistent with electronic structure. So this means that you keep doing this cycle until U and V values do not change and your geometry doesn't change. So really sort of driving your system towards global extremum. So there is no theorem for the moment. It's just our statement based on our experience. So we're trying sort of minimize or extremize the functional. So we're doing it, let's say, by hand, by doing iterative calculation. But yeah, so this is what we're doing. And then you say, okay, now I reached self-consistency where U and V do not change anymore, and my geometry is also converged. But to do structural optimization with DFT+U plus V, you need compute forces and stresses. And in the framework of DFT+U and plus V, you have extra contributions to forces. I don't have time to go into details, but if you're interested, we can talk more during coffee break. But it can be shown that to compute extra contribution to forces called Hubbard forces, you need to do quite a lot of math, and you actually face a problem that you need to compute this object, which is the derivative of the inverse square root of the overlap matrix with respect to displacement. It's not a function, so it's not easy to compute this object. It's a matrix, and it's not trivial how to compute it. But thanks to our colleague Francesco Culante, who is a chemist and good mathematician, he actually came up with a very nice exact solution where we need to solve so-called Lyapunov or Sylvester equation written here, where in green I highlight the object that we want to compute. And we can solve this equation and write actually the exact solution of this in this form, integral form. But you can actually follow another path because Stefan and Emine, they had some somewhat different idea in terms of eigenvalues. And actually, then Anton and his group also followed the same path that you and Emine proposed, while Francesco had somewhat different way. Anyways, there is exact solution to this equation, which can be written in this compact form. All what you need is just this, so basically Z, which are these eigenvalues of this matrix, and eigenvector, if I call it correctly, eigenvalues and eigenvectors. That's all what you need to do. And this is implemented in quantum ESPRESSO. And if you compare the forces using this exact analytical expression, you obtain this column. And if you do it with finite differences, you get this. And the agreement is just extremely good, which confirms the correctness of the equation and correctness of implementation. You can do the same for stress, but stress tensor, which is much more complicated, so I don't want to talk about that. Sorry?
More stressful.
Exactly, more stressful for me and for you. So we're already stressed enough. So let's just take home messages. So I really hope that maybe you forget all what I said, but I hope that something remains in your mind. So basically, DFT+U and +U+U are accurate and computationally efficient approaches to correct interaction errors and not strong correlations in transition matter rarest compounds. Hubbard parameters are not universal. So this means don't take some random U from some random paper. Just first check which code they used, which Hubbard projectors they used, etc. Because it's really a very common mistake. Some people computed U with VASP, and then you go and use the same value of U with Advanced Quantum ESPRESSO. This is not correct. Hubbard parameters can be computed from first principles using different approaches, but in particular using linear response. We developed very nice, we reformulated nicely the way to compute Hubbard parameters using DFPT, pioneered by Paolo, Stefano, Baroni, Stefano De Roncoli, Andrea Del Corso. And Hubbard parameters and projectors must always be consistent. Thank you.
Thank you very much. Questions?
Yuri, I vaguely remember that there is another animal in the zoo. It's double counting. What is the state of the art? Do you have any idea what is implemented in quantum ESPRESSO? What could be done? What alternatives are there?
Okay, so I think Matteo and Stefano are more experts, but there are two most popular double counting. So let me just put it in context for everyone. I don't have the slide with where the Hubbard correction written as a sum of two terms. Hubbard terms plus minus double counting. Okay, let's stay here. Yes, so what is double counting? So this is already the final expression, but you can write it as two terms. One is the Hubbard-like term, and second is the double counting. The double counting is the term that we're subtracting because we're adding the Hubbard term. So we cannot simply add some amount of energy to the DFT energy. DFT energy is already complete. We cannot add or remove amount of energy randomly. So if we're adding a Hubbard term, we need to actually remove the double counting. So what does it mean, double counting? So with the Hubbard correction, with the Hubbard term, we want to describe better the localization of the electrons. But that is already contained in DFT in a wrong way, in some mean field average way. So we need to subtract that amount of wrong description. And we call that double counting term that we remove. And there are, so this is arbitrary. There is different ways how to define double counting. There are two options. The most popular one is called fully localized limit, and second around mean field. So here we're using fully localized limit. It's like adapted for opening gap in mod Hubbard insulators or charge transfer insulators. While around mean field, it's another type which was developed for metallic, truly metallic systems. So here we're using fully localized limit in quantum ESPRESSO. Around mean field is something else which we don't really like. First, because DFT+U is not really efficient for metals. If you take a true metal like strontium vanadate, so Tommaso, it's more expert. If you apply DFT+U to true metal, it doesn't do anything almost. There's little change. So there is DFT+U omega after the coffee break. Maybe Tommaso will expand it. But basically, around mean field and DFT+U for metal, something, in my opinion, as far as I understand, is not something worth it. So we don't have that. And also, if you look at the DFT+U as the method, the pure self interactions, there is no round mean field there. So somehow, very interestingly, if you do Hubbard plus fully localized limit, you end up with this very nice expression, which can be actually derived from different perspective, completely different perspective. But you cannot do the same with round mean field. With round mean field, you obtain some final expression, which I think will not correct self interactions. Actually, Edward can maybe also explain more. I don't know where is Edward. Yeah. So that's the state, and then you can mix around mean field and fully localized limit. You can mix them, and I think Matteo even did something more advanced, some kind of fancy mixing, so to have both worlds in the same thing. And I think Matteo has even a private version of Quantum ESPRESSO with this more flexible double counting.
Yeah, I guess the really nice one. When you does depend on the way you consider the double counting or
Yeah,
it's the you don't see.
I think that what doesn't change is the fact that we take about at the end the quadratic says, but so we not going to change the
great. I never used around mean field in my life, so I don't have any experience with it.
Yeah, this version basically does as a positive penalty in energy for occupation in 0 and 1. So anything that's fractional is this storage. With the different version, we might get like kind of action of the equivalence to
It's
a lot of nice stuff. My question is regarding the projectors. So, is there a stronger reason you think that? I mean, is there the case that there exist systems with like crazy hybridization that you having like not even DFT+U+C using atomic local atomic orbitals, which provided the description for those. And is there like a good enough strong reason why you believe it would justify implementing the functions to your HP code? Like, would they provide a advanced description of your local orbitals in this case that you can support?
Yeah, no, I understand. Yeah. So first, it reminded me that I forgot something important. Between these two types of projectors, the second one is better. The orthogonalized one is better because in the first one there is an issue. So imagine two atoms and orbitals overlapping. So if you apply the Hubbard correction to this and to this, it's fine. But what happens in the overlap region, that Hubbard correction is applied twice, which is not good. It's sort of double counting, but not the double count we just talked about. So in this approach, there is sort of applying U correction twice in the overlap region. While if you orthogonalize orbitals, you don't have this problem. So this is better, and from our experience, it gives more accurate results. Then, do we really gain anything if we go from orthoatomic orbitals to maximum localized? So if you localize these orbitals on atoms, I think you don't really gain any much, almost nothing. I would say maximum localized function should be equivalent to orthogonalized atomic. They're slightly different, but they're very, very similar if they are atom-centered. But what is interesting, what would be interesting to try, I mean, you can localize many functions on the bonds in the interstitial regions, not atom-centered, but between atoms. Let's say in strongly covalent systems, the charge density can be, it's high between atoms, not on the atoms, but between atoms in strongly covalent. So we can build the Wannier functions exactly on the bond, and then in principle, we can apply effective U on that Wannier function, and this would replace atom-centered U and be between atoms.
Yeah, but isn't it what you wrote this B is doing in this case?
I think we don't need B in that
No,
case.
yeah, so like this role that you're describing, isn't it what you would hope B to do in the atomic orbital?
Sorry,
Yeah, because like.
Yeah, but I don't know. I don't know if you can go. Can you go next slide? The way where you show the V exactly. Yeah, exactly. So when you, I mean, I understand the piecewise linearity argument. Actually, we made it, and in which you say I'm occupying one level, and then I want the energy to be linear or excluding the unstructured term, etc. So in a certain sense, the projector, but on which orbital do we project? If we take atomic orbitals, this is not probably the correct one. So but somehow, if you change projectors, so I don't understand in a certain sense what is the justification of the V things, because V things is not a interaction terms, it's the interaction between. So I see V maybe as what you need because your projector is not the right one. So if you modify the projector to be the orthogonalized orbitals, which is better, your V term is actually going down, no? Goes from 1 to 0. And maybe the ideal, I don't know if the ideal is the maximally localized one, would have V equals 0 and whatever. So would put all the emphasis on the self energy of the right orbital, and then what do you think about that?
Yeah, I think I agree in the sense that you may think of doing the U only version of Wannier function, maximum Wannier function.
Should different projectors shift U to V, and so maybe you want to have everything on one single orbital, and this would be the optimal projector, which might be the maximum localized function of something even more complicated.
Personally, I don't see the straight equivalence of having something that is fully localized and something that is localized plus nearest neighbor.
No, but I'm saying
So I kind of
your orbitals I mean, you have an atom with localized orbitals, but in an environment, and somehow this modify the localized orbitals. As we said, this then concentrated on the orbitals that you would have in the isolated atom is not good, or may not be good, and may be better to orthogonalize, or it might be better to find the best localized orbital in the system that might be the maximum localized orbitals. And if this is so, if this is the right projectors, then should address the self energy of that orbital only. It wouldn't need to make inter site correction if the does basically correct the on-site. That could be on-site or on bond. I mean, if the right localized officer is on bond, then the right projector should be on the bond.
Actually, that is what most open not only, but the thing with group of correction is always on site, so on all of it.
Yeah, Matteo, but I don't also comment.
Yeah, I just want to complete what Stefano was saying. I think it's I mean the spirit of the V is exactly this one. I mean to make localization more flexible and to avoid having to really find the projectors basically each time. So if your system likes to localize electrons on bonds, either you use the localizing function centered on bonds and you do U only, or you try to use the standard definition and the standard atomic space, but in a sense, if you have a U only on bonds and you rewrite everything in atomic basis set, you get on-site terms plus something else, and we assume that the next important term that you get is the one captured by the V, the intersite. It's probably more. It's probably more that which we don't have in the V formulation, but which will have the next.
Okay, just if I can just comment about this very quickly. So just my understanding of things with this simple cartoon. Yeah, here. So this cartoon. So I mean, you can do whatever you want. Just I want to preserve the covalency. So this covalency, this is a sort of hybridization, which is in nature there is some hybridization. So we can do whatever we want, but I want to keep it there. So if I use atomic orbitals and just U, I would push too much, and as I increase U, the 10 eV and until infinity. So in the limit, I will go to the sharp case, and I will kill that. That is wrong. So that means, okay, I need to put plus V to have somehow restore back this covalence. Now the question is, what do I have if I have maximal plasma function? Do I need V or is it 0 V? Well, I don't know, but if V is 0, this means the Wannier orbitals are such that they still have that nature of covalency somehow. I don't know if this makes sense, but to me, if you have 0 V in the basis of Wannier function, maximum Wannier function, it means your Wannier functions are such that you have that covalency there. If instead you with Wannier function you still lose some amount of covalency, which is naturally should be there, then I think you would need some finite value of V still to restore it back. I think it's all about if there is a covalency in nature, you should still have it, whatever orbitals you use. I don't know if this makes sense.
This is a bit misleading. Silicon, you just have that one big in the middle.
Exactly. So in silicon, you can have Wannier functions in sp3 between two atoms. So have 0 here, but you have really Gaussian between atoms. So have just one Wannier function. If U effective, so U effective instead of U and V local, U local and V between atoms. So you have U effective, which is sort of mean value with in the basis of this Wannier function, which is between two atoms. I mean, this is just speculation, but we really need to do some experimenting and really see if this works.
Oh yeah, it's a kind of a follow-up on this topic, because I was wondering, I mean, also in the original formulation you had, if I'm not mistaken, an infinite sum. So here we are assuming that the complete basis factor is like with the orbitals, but then you're starting out in the overlaps in the covalent bonds. So what do you think is the direction to go, either Wannier functions Well, maybe you just select some of them, or like I think there was also a work from Matteo where they also started using suborbitals and overlaps between them. So like you start adding more projectors if you want also on the s orbitals and the overlap between them. So these things, I don't know.
Well, no, I think the direction with maximum localized Vanilla functions is a good one. Because first of all, Vanilla functions are maximum localized Vanilla functions are used everywhere now. The condensed matter, so it's elegant and it's very flexible, and we have very precise ways to compute them. So I think it's good direction, and it's also you can localize them where you want. I mean, if you want on the atom, you have it on the atom. If you want on the bond, you have it on the bond. You can really have a lot of flexibility. So I think it's very nice. And then what you mentioned, the second part that you have not like the frontier orbitals, let's say the 3D shell, the frontier orbital here, and 2p orbitals of oxygen. So these are both frontier. But you are saying, okay, in 3D, in the transition metal I have 3D, but then I have background, I can call it background, which is 3p, 3s. In oxygen, I have 2p, which are frontier, we have 2s. You can have this background, then frontier, background, these cross terms. So yeah, this is what Matteo implemented. So I don't have really experience with that, but that's maybe you can comment. It's for sure more flexible, more degrees of freedom to play with. I don't know if it's important, maybe in some systems. I think it's important when you have light elements like p-block. In that case, I think, yeah, you need that, like gallium arsenide, silicon, you really need this kind of cross terms.
Yeah, we needed that mostly because of SP3 dispensation. Without having those two channels, the atom will get the I think that Vanier might be interesting also because give a better justification of the use of these double counting that tries to fully maximum localize and function the localization.
Do you know the way to calculate the exchange parameter J from the first principle?
In this context?
Potentially in this context. So I know U and V are important, but in some cases, like for rare earths, the J parameter has an explicit term for that might be important.
Oh, okay, okay. So we just need to understand which J parameter you're talking. Is it Heisenberg exchange J, or is it the J? I think you're talking about DFT+U plus J, this liquid. Okay, that. So yeah, I mean, Matteo published a paper like more than 10 years ago where they also tried to use the same approach, linear response theory, to compute J, and they did it for copper oxide because it was non-magnetic. But then, if you try to compute J with linear response theory for magnetic materials, there are some convergence issues and some, but also there are conceptual issues. I mean, we can talk with Edward more. So there are some, let's say, work to do. And actually, there is another function called DFT+U plus J0, which was proposed by Matteo. But that function seems to have some issues if you see this method as the method that restores plane wave condition. Actually, it's not just piecewise linearity, but it's plane wave. So essentially, to cut long story short, there is still work to do for J. Yeah.
Okay, so I think we thank again Yuri.